Hey guys, happy Tuesday. Today we're going to talk about our final concept, which is relating delta G and the spontaneity of a reaction to equilibrium and the equilibrium constant. And so here you can see we have our reaction between hydrogen gas and oxygen gas to produce water at 298. And we can see that that reaction has a delta G of negative 458 kilojoules. So we know that this reaction is spontaneous. Right. And then here we know that if we look at the same reaction, we can see that that same reaction has a K value of 1.92 times 10 to the 80th. And so in this case here we see K is also a lot greater than 1. And so what we learned in equilibrium is that we would say that the forward process is favored. And so we can see that, and that's what we would expect, right? Because if delta G is spontaneous, we're expecting that reaction to go forward, right? And so there should be some relationship between the two values, right? And so if the reaction is spontaneous, then we would expect the forward reaction to be favored through equilibrium, okay? And so how does this all work, right? And the other way we can look at it is through equilibrium. We know that we have this delta G naught, and that little naught sign tells us that they're in their standard state. And since they're in their standard state, what that truly means is that we would have each of these particular things in here at 1 atm. This is at 1.0 atm, and this is at 1.0 atm. So all these gases are in their standard state at atm. Well, if we kind of think about this in terms of equilibrium, we know that, okay, well, K obviously is equal to 1.92 times 10 to the 80th. And now Q, which is, again, if we don't know that the reaction's at equilibrium or not, we can check the reaction quotient. And here we could get 1 squared over 1 squared times 1 for whopping 1. And so in this case here, we see that K is greater than Q. And we know that when K is greater than Q, the reaction will shift forward. Okay, and so the reaction would shift forward, which means it would have to go in that direction that way, which again relates back to it being spontaneous, right? And so in this case, we have K being greater than Q. When K is greater than Q, we know Q has to get bigger to reach equilibrium, and the only way that it can get bigger is for that reaction to shift forward. So what this means for us is that we know that if delta G naught is negative, then we know K will be greater than 1. Well, let me change that symbol. K will be greater than 1, right? And that is going to be true. If it's negative, then it must be greater than 1. If delta G is positive, we know K is less than 1, right? And then if delta G naught is 0, then K would be equal to 1, because the natural log of, well, we'll talk about that in a little bit, okay? So these are some things to remember, especially as you work through some of these problems, right? So if delta G is negative, K has to be greater than 1. If you get something different, then you've probably done something wrong. Now, these reactions, when we look at that, assume that things are in their standard state in the case of gases at 1 atm. But quite often, we don't work with gases in their standard state, or any reactants in their standard state, really. And so the question becomes, well, would the value of delta G change if the gases were not in their standard state, right? So for instance, let's say that we had a reaction that's been occurring for a little bit, and we see that we have these for our pressures for each individual thing. Now, one thing that we learned before, right, is we could say, ooh, well, Q in this case would be equal to, again, 1.63 squared over 0.0785 squared times 0.587, and that would be equal to 6.599, right? And again, we know now K is still greater than Q, so the reaction's still going forward. But again, right, as Q gets bigger, when Q equals K, we know that the process has reached equilibrium. And so now we're a little bit closer to equilibrium. And the closer that we get to equilibrium, the lower the value of delta G becomes. Because remember, when we hit equilibrium, delta G equals 0. And so how can we figure out the new value of delta G? Where is it at? How close is it we got to 0? Well, we can do that by using this formula here, right? We have delta G equals delta G naught plus RT natural log of Q. Well, Q is there. Delta G is when we're in our standard state at a particular temperature, right? And we're not expecting that to change. So this will be our non-standard state delta G. We know T is still in Kelvin, and R is going to be 8.314 joules per mole Kelvin. But in this case here, since delta G is usually in kilojoules, we're going to use this as 0.008314 kilojoules per mole Kelvin, okay, just to make sure that we're doing that right. So this would work kind of like this, right? And so we would have our delta G is going to be equal to our delta G naught, which we know is 458, plus R, which we know is 0.008314, T is 298, and then the natural log of Q, which we just figured out up there, is going to be, it's, well, it's going to be, I lied, this is not actually what Q is, but anyways, delta G is going to be equal to this negative 458 plus this is 2.78 now times, and the natural log of Q actually works out to be 6.599. So that would be E to that. So that's my fault. And so when we look at this delta G and we do that together, we're going to see that that's going to be a negative 441.6 kilojoules. So again, our delta G became more positive, right? Because we're shifting more towards equilibrium, and it's going to start approaching 0 in this particular case. Okay, so but this is how we can figure out what the new value of delta G is when we're in our non-standard states. Now, here's the kicker, right? We know eventually that this value will get down to 0, right? Because delta G will be 0. And we know that, okay, if this particular thing goes down to 0, we know at that particular time we are at equilibrium. And, right? And we know once we hit equilibrium, Q is equal to K. And so what we would have here is, well, 0 would equal delta G naught plus RT natural log of K, which means here we would get delta G naught equaling a negative RT natural log of K. And so this is another great equation for us to use, because if we know delta G, then we can figure out the equilibrium constant for that particular reaction. Or vice versa, if we know the equilibrium constant, we can figure out delta G naught. So in this example here, we have the synthesis of ammonia from its elements. We see that this is at 298. And we see that it's a spontaneous process, delta G is negative. And so if we want to know what the value of K is for this, we can just plug and chug, right? So we would know that, oh, delta G naught equals negative RT natural log of K. Negative 33 equals our 0.008314 times 298 natural log of K. We're going to see if we kind of do our math, the natural log of K is going to be equal to 13.32, and then K we know would equal E raised to the 13.32, which is going to be equal to 6.09 times 10 to the fifth. And again, right, we're expecting K to be greater than 1. Notice that K is, or delta G is not as large, right? So it's not as big as a negative number, which means that K is not as big, right? Negative fifth as opposed to positive 5 as opposed to positive 80 up above. Okay, and so this reaction here, again, is going to be really good and useful for you to know. Okay, let me know if you guys have any questions. I'll be available tomorrow during Teams. Make sure you're working through those practice problems. All right, guys, peace, love, happiness. Thanks for playing.